On slide 122, I turn to the important question of how large n and t have to be in your DSEM analysis. And I'm going to show you Monte Carlo simulations for both two-level and cross-classified DSEM. But first, on slide 123, here's a checklist that you may want to take a look at before you contemplate DSEM analysis. First of all, do you have enough time points? And we recommend at least 15 to 20. And if you don't have that, you might instead want to do a single level wide analysis. And you want a little bit more, at least 25, for good performance with random slopes and variances, the random effects beyond the random intercepts. That requires more time points. And at least 50 for good n equals 1 performance, although we saw that we had an example for one person with 46 time points, and that where the results look good for a very simple model, however. Now, another important question you're going to ask yourself is, do enough individuals have enough time points without missing, particularly in the context of using the t-interval option, which inserts missing data rows? And if you don't have that, random slope and variance estimation can be problematic. And also, does your outcome have variation across time? And that's, after all, the central part of your analysis, why you do the analysis. And you may want to consider deleting individuals with no variation. And do you have enough individuals for random effects modeling on the between level? You know, on the between level, you can formulate a full SEM model if you want to. And we recommend a minimum of 50 people, but many more may be needed for certain parameters like between level variances. Variances are particularly hard to estimate well. And in the simulation that I'm going to show you below, I needed 500 people. And you should also ask yourself, does your outcome have a strong trend that should be modeled? If yes, use RDSEM with a function of time as a covariate. Now, all of these points here on the checklist depend very much on the specifics of the model. And if you want to go a little deeper and get a little bit more of insight in what you need for your situation, you want to do your own Monte Carlo simulation. And it's not hard. On slide 124, I point out that some Monte Carlo work has already been done in this area by Schultzberg and me in 2018 in the SEM journal. And we looked at 9 different kinds of univariate DSEM models with varying complexity. For instance, a univariate model with random intercept, random autoregression, and random residual variance turned out to need 25 time points for a sample size of 150 and 50 time points for a smaller sample size number of people. Now, what is worse than, I'm quoting from the paper, having a lower n or a lower t? Can large n compensate for small t better than large t can compensate for small n? And it seems like large n is better. With that said, the random, autoregressive, and residual variances do need fairly large t to be well estimated. So if the autoregressive or residual variance is of substantive interest rather than just a heterogeneity feature to control for, many repeated measures would be needed. So there's a lot to learn from that paper, but your situation is still probably quite different. In the current study we have 240 people and an average of 24 time points. So by the rules up here, it seems like it would be sufficient for a univariate model, but is it sufficient for a multivariate model like the bivariate models that we have looked at? So we turn to doing our own Monte Carlo simulation. And we can do that if we have some initial DSEM work, initial DSEM analysis that can give us parameter estimate values that we can save by using the S values option in the output in the real data run. And I did that for the step 4 model 2, the lag 0 effect of tired influencing positive affect. So I put in the 250 observations and 25 time points, which is the average number of time points for the people. So the Monte Carlo command then specifies the, starting really here, 250 people observed over 25 time points, each one of them 25 time points. If you multiply that, you get the total number of observations. And if you make a mistake, Mplus will tell you. And I work with 500 replications. Often I start with 100 or even one replication. Usually I start with 1 to see that I specify the model correctly. And then I go to 10 to see that I get roughly the correct estimates. And then I go to 100, and then I do publication quality with 500. So here I have number of cluster sizes equal 1. There's only one size 25. I have the lagged option here, signifying time series analysis, DSM analysis. And commented out here are various ways of saving all of the replications if you want to, or saving one replication if you want to take a look at the values for one replication. I do 2-level analysis here, estimated base, the usual base specifications, and I have a model population and a model. And I usually just copy over the model population into the model section. So you have the autoregressive feature and the contemporaneous lag 0 effect here, and the lag 1 effect, and you have the autoregressive for tiredness and the cross-lagged effect for tiredness. And on between you have those coefficients. So all of these values then you get from S values and just copy in. So it's very simple to do. So what I found here, based on these estimates for 250 people, 25 time points, excellent results in terms of the parameter estimates, in terms of the standard errors, and in terms of the coverage. Now, if I went down to only 15 time points, well, I would call them good results. Not excellent, but good results. A little bit low coverage for tired's autoregressive effect, for instance. But not terrible. Going down to 10, not acceptable results. So this would agree with the checklist points that I gave you earlier. Now, a more realistic analysis would be obtained with varying cluster sizes. So we have individuals with different number of time points. Now, the real data has maximum 84 time points. This is with t-interval 2. An average number of time points 24. That's why I went with 25 here to round it off. Now, an approximation to this situation, one can do this in many different ways, but a very simple way to approximate this picture with people having different number of time points is to take, say, 5 cluster sizes. So here I say that we have 10 clusters of size 5. So that's a little low. Only 5 time points, particularly if you have a model with 9 random effects, but you want 10. You have 65 clusters of size 15, 100 clusters of size 25, so that's the average. 65 of 50 and 10 of 80. And I ran that then, so that's the same as n equals 250, but then varying number of time points from 5 to 80. Still have excellent results in terms of estimates, standard errors, and coverage. Now on slide 127 then, I bring in random slopes, random effects. So parameter values are then again using S values based on step 4 model 1 with added random slopes, random variances, and random covariance. So that's that model with many, 9 in this case, random effects that we talked about. So this is a more complex model, and I used 250 people and the 5 cluster sizes that I had on the previous slide. And actually I could get good results here, except between level variances have somewhat biased estimates. The estimates are too large, as you might imagine with a variance distribution with a long right tail. Biased estimates and biased standard errors. And it turns out that if I up this to 500, double the sample size, then those biases are, if not totally disappeared, they've gone down to be ignorable. Now you may not be that interested in these variances. I don't know. It depends on what the substantive question is. Now, in doing this, in doing simulations with random slopes, you have to be aware of an issue here. And we have implemented a new feature in version 8.9, which comes out when you ask for Tech 9, which you should ask for in Monte Carlo simulation studies. So in this case, it says 351 clusters were removed because the generated random effects produced non-stationary time series or non-positive definite covariance matrices. So with random slopes, variances, and covariances, non-stationarity is quite likely for some clusters in some replications. And that created havoc in the past in simulations in 8.8 and earlier. Those replications were deleted. So you could end up with, say, getting only 100 replications out of 500 that are summarized. So low percentage of reported replications. So that is not a very useful Monte Carlo study. Now, however, the cluster is thrown out that has this problem, the non-stationarity problem, but the replication is kept. You know, it can be very few or only one cluster in a replication that has this problem, and that shouldn't hurt the whole replication. 351 may sound like a lot, but it's less than 1% of the total generated number of clusters. You know, 250 clusters, so number of people, times 500, which is the number of replications. So this is actually an ignorable problem. And now we get 100% of the 500 replications reported. Now, what do we do with cross-classification? Cross-classified Monte Carlo. Well, that's not hard to do either. Once again, drawing on S values from a real data run. The specification of cluster sizes is a little bit more complex here. There's a bracket approach used, but it reads the same way. You have 10 clusters of size 5. We'd only draw one person in this combination of time and ID classification. 65 of 15, 100 of 25, etc. Just like before. It's just specified, expressed in a slightly different way. The number of cluster sizes is 5, and we don't have to worry about this number. You could have said 1 here as well, but that would take us deep into details of C sizes that you can read about in the user's guide. But 5 corresponds to the 5 different cluster sizes. So we do cross-classified analysis, and everything on the right here is obtained from S values in the real data cross-classified run that we did. It's the lag 0 run that we talked about. And I'm only giving model population here. You also have the model, which is just a copy of this. So you have PA on tire, the contemporaneous effect here, for instance. Now the new thing is that we have 2 between level 2A and 2B. And we touched on that a little bit when we talked about plots. And here is the key issue. In the S values from the real data run, it says between time. And that has to be replaced by between level 2A. So 2A is the time dimension. And between ID has to be replaced by between level 2B. So that you have to do yourself. changing that here and there. And this run also showed excellent results. No problems in the output. It takes a little bit longer, and therefore I went down to 100 applications. But of course you can do 500 easily if you just, say, run it overnight.